Hi, I'm Bo. In this video, I will be going over some common data structures and algorithms in JavaScript. I'll be showing you how to implement them in JavaScript. So if you want to see the exact list, you can check the description, and I have links to all the code in the description as well. So let's get started.
A stack of books is a great example of the stack data structure. If you make a stack of books, the topmost book in the stack was the one that you put there last. If you remove that book from your stack's top, you would expose the book that was put there before the last book. Stacks are a last in, first out type of service. The last book you put on top of a stack would be the first book you take off the stack. Another example of a stack is your browser's back button. If you look up here, we just opened up Facebook.com, so we add it to the top of the stack of sites that we've already visited previously. We do stack.push. Push is one of the stack methods. You push Facebook on top of the stack. This middle is what it looks like when we are visiting Facebook, and then this bottom image is where we press the back button to navigate back to Twitter. So we pop off the most recent URL, and we just leave Twitter at the top of it. The functions traditionally provided in the stack are push for placing data onto a stack, pop for removing the top element of a stack, peek for displaying the top element of a stack, and length or size for determining how many elements are on a stack. A nice feature of JavaScript is that the array object already has all the functions we need in order to use it as a stack. So you could just use an array as a stack. I will show you how to do this using an array, but then I will actually create a stack class and show you how that works too. I'm going to use an array stack to find words that are palindromes. A palindrome is a word that is spelled the same forwards and backwards, such as Bob, B-O-B, or race car, R-A-C-E-C-A-R. Okay, so we have var letters equals an empty array, and that's the stack. Because remember, I said arrays have all the functions of a stack. So look at how this program works. First, we're going to set a word to be any word we want, and we're going to choose race car, which is a palindrome. And then we are going to have a variable, which is just a empty string for our word, or reversed word. We're going to use the stack to fill up the our word variable with the reverse of the word variable. The first thing we're going to do is put the letters of the word into the stack. So we have a for loop here, and we're going to start at index 0 and go to the last index of the word length. So an index in a string is just which character we're looking at. So we're going to do letters, which remember is our stack, dot push, the stack function where you push something on top of the stack, and we're going to push word index I. So that's just going to take this for loop is just going to take each letter of our word, because we have index 0, index 1, index 2, each letter is a new index, and push it onto the letter stack. Now we are going to pop off the stack in reverse order so we can create the our word variable, which is the reverse of the word variable. Another for loop, and now we are going to have the our word, and we're going to add one letter at a time from the stack by popping off the top letter. And because they were put in order, they're going to be popped off in reversed order. Now we have a string that should be the reverse of the first word. So word and our word should be reverse of each other. Now to check if it's a palindrome, we just say if our word equals word, it is a palindrome, or else it's not a palindrome. So let's run that and see what happens. And race car is a palindrome. But if we change that to freeCodeCamp and run that, nope, it's not a palindrome. Okay, that was just a basic usage of a stack using an array. Now I will show you how to implement a stack in JavaScript so you can understand stacks a little more. You probably would never do that because you can use an array as a stack, but this should possibly help you understand how stacks work a little better. So here's where we're going to create the stack, which is going to be this function here. We're going to have two variables, this.count and this.storage. Now this.storage is an empty object, and count is going to keep track of how many items are in the stack. So here are all the different methods. We have push, this.push is going to add a value to the end of the stack. You're going to pass in the value. This.storage, remember storage is the empty object. At the index this.count, we are going to add the value. So we're going to put the value on the top of the stack or the end of the stack, and then we're just going to increment count up one. So now it's showing that we have another item in the stack. The next function, we're going to remove and return the value at the end of the stack or at the top of the stack, which is this.pop. This is going to pop an item off. So if this.count equals 0, that means there's nothing in the stack, and we're going to return undefined because there is nothing in the stack. Once we return undefined, we're not going to do anything the rest of this code here because we've already returned from this function. If we're popping off something, we're going to have to decrement the count. So it's a count minus 1, so 1 less. We're going to set the result to this.storage, which is the object for our stack, and at index this.count, which is the last item in the stack. And then we're going to delete that item, and we're going to return a result. So you get the last item back, but it will be deleted off of the stack. And there's just a few more methods. This.size is going to return this.count, which is the number of items in the stack. And then the last function is this.peak, which is going to return the value at the end of the stack, but it will not remove it, like pop. So peak and pop are kind of similar, but pop removes the item and peak does not remove the item. So return this.storage and then this.count minus 1. This.count would actually be the index 1 after the final item, because that's where you would add a new item, but you would have to do minus 1 to get the last item. And if you're peaking, you do not want to pass in a value. So let me take that off there. So you only pass in the value when you're pushing in something. Let's see how this would work down here. Okay, we are going to create a variable called myStack, which is a new stack, which is what we just defined up there. We're going to push 1 onto it. To the top, then we're going to push 2 on the top, so it's just a stack with 1 and then 2. We're going to peak, and we're going to have to console.log this because it's going to just return the top number of the stack, which should be 2. Now we're going to pop off 2, so it's going to return 2 again, but it's going to remove it, and then if we peak, we should be back to 1. And before we run that, I forgot these extra parentheses here because these are functions and you need the parentheses at the end of all functions. So let's try that. Okay, see, we peaked at 2, we popped off 2, and then when we peaked again, it was 1 because 2 was removed. Now you can also add other things to the stack. Now we're going to push a string onto the stack, and we're going to check the size, then we're going to peak, and then we're going to pop it off, and then we're going to peak again. So let's see what that does. So we pushed 1, we pushed 2, we peaked, which showed 2, we popped, which popped off 2, we peaked again, which showed 1, so there's only one thing in the stack, then we pushed freeCodeCamp, the string, and we console.log the size, and now the size is 2. The stack is just 1 on the bottom, and then freeCodeCamp on the top. We're going to peak, which is going to show freeCodeCamp. Now we're going to pop, which is going to pop off and show freeCodeCamp, and then we're going to peak again, and we'll see that it's just 1 on the bottom. Well, those are the basics of stack. The set data structure is kind of like an array, except there are no duplicate items, and the values are not in any particular order. The typical use for a set is to simply check for the presence of an item. I'm going to show you how to implement a set function. ES6 actually has a built-in set object. However, the built-in set object does not contain all the methods that are common to sets. So you may still have to implement part of the set yourself, depending on what you're going to use it for. When I show you the implementation for the set, I will tell you which methods are part of the ES6 set and which are not. So we're just going to go through this code. We're going to call it mySet. Now we could call it set, but I want to make it different than the ES6 set. So this is my set. So here's just the collection. The set is going to be a collection of items, and we're going to store them in an array, which an array can have duplicate items, but we're going to implement this in such a way that you cannot add duplicate items to this array. This method, the method has, is going to check for the presence of an element and then return true or false. So you're going to pass in the element, and it's going to do collection.index of element is not -1. So if the element is not in the collection, it's going to return -1. So if it doesn't return -1, it's true. So if it's not -1, it's true. That means the element is in the array, else it's false. Now we have the values. This is going to return all the values of the set. Pretty straightforward, just return the collection. Now we have add. We're going to add an element to this set, but first we have to check if the element is in the set already. So we're going to call the method we've already defined, the has method, and see if the collection has the element. If it does not have the element, then we can add it. We're going to push that element to that collection array, and we're going to return true. Else, we're going to return false. So if we don't push an element to the collection, we're returning false. Now we have remove. This is going to remove an element. So first we have to check if the element is in the collection, and if it is in the collection, we're going to find out what the index of that element is, and then we're going to remove it. Splice means we're going to take out an element in the array starting at the index of the element and going for one element. We're going to take out one element, and then we're going to return true, or we're going to return false if that element is not in the collection. Then we're just going to return the size of the collection. We're just going to return collection.length. Every method we've gone through so far is in the ES6 implementation of the set. So the ES6 set has values, add, remove, and size, except remove is delete. In the EX6 set, instead of calling remove, you're going to call delete. But all the other things are included. Oh, another thing is size is not a method in the ES6 set. Size is a property. That just means that when you're calling it, you're not going to put parentheses after the method, because it's just a property. So you can do set.size instead of set.size with parentheses after it. Okay, now we're going to get into the methods that are not in the ES6 implementation of the set, but are often included in sets. The next few methods actually just help you work with sets and when you're working with two different sets. So we have union. This method is going to return the union of two sets. So it's going to combine the sets but leave out any duplicates in the combination of the sets. So we're going to call the union method on the original set, and we're going to pass in the other set that we want to combine. We're going to create a new set, which this should be my set. Same with down here, because we want to make it distinct from the ES6 set. So we have the union set, which is just a new set. That's what we're going to combine the sets into. We have the first set, which is this.values, and the values, we're just calling the values method up here to return the collection. And the second set is going to be the other set.values. We're going to do first set for each, and for each value in that set, we're going to do union set.add to add the value. Then we'll do the same thing, second set for each, and for each value in the second set, we're going to add the value. Remember, the add method already does not add the value if it's a duplicate. So the union set now will not contain any duplicates. And since for the set data structure the order doesn't matter, we don't have to have the values in any particular order. And then we're going to return the union set. Now we have intersection, which is going to return the intersection of the two sets as a new set. So we're going to make a new set here. Intersection set equals new my set. The first set, again, we're going to call the this.values to get all the values in the first set. Now, for each value in the first set, we are going to check if the other set has the value. We are going to add it, and then we're going to return the intersection set. So the intersection is just all the items that are in both sets, and we're going to return that as a new set. And this next function, we're also going to have to add the my there. So this is the difference. So the difference between the sets. So all the items that are in one set but not the other set. So we're going to create a new set again, the different set, and again we're going to get the values of the first set. Now this is very similar to the intersection. We're going to go through each value in the first set, and if the other set does not have the value, remember up here we were seeing if the other set had the value. Now we're going to use the not operator, the exclamation point, to see if the value is not in the set, and we're going to add that to the difference set. Then we'll return the different set. And the last method we're going to talk about is the subset. And this is going to test if the set is a subset of a different set. So it's going to test if the first set is completely contained within the second set. So it's just going to return true or false. So we're going to pass in the other set. We're going to, again, get all the values of the first set, and we're going to call this function firstSet.every, and what the every method is going to do is going to test whether all the elements in the array pass the test implemented by the provided function. So we're going to test if all the elements in the first set will pass this function, which is otherSet.hasValue. Are all the elements in the first set, are they in the second set? So we're going to see if the first set is a subset of the second set. So that's the set data structure. And let's quickly just show you some uses of the set. So we have set A is new my set. Set B is new my set. We're going to add to set A. We're going to add to set B. We're going to add to set B, C. We're going to add to set B, A. And we're going to add to set B, D. And now we're going to see if set A is a subset of set B. So is every item in set A, which is actually just the letter A, in set B, which it is because it's right here. Let's run that, and it should say true. Let's do some other things. Okay, and this is the set A.intersection set B is going to return a new set, which we're then going to call the values function, so we can see all the values in that set. And it's just A, because the only value that's in both set A and set B is A. But we can do a lot of the same things with the built-in set. I'm going to copy all this. Instead of calling this my set, we're just going to have set. We're going to do set C and set D. Okay, so here's one difference with the ES6 set is that when you call the values method, instead of returning an array, it's going to return an iterator. So you can see object set iterator here, and then you can still iterate through all the items in the array. Besides that, all the other methods that a set has are very similar to the set that we implemented. So we can do set d.delete. Now this is instead of remove. So we're going to delete the A, and then we're going to console.log and check if set D has A. And we can see it's false because it's been deleted. And we can also try to add D, which is already in the set. Oh, and there is one final thing that's different with the ES6 implementation. The add method is not going to return true or false whether the item has been added or not. Besides adding the item, what it's going to return, so what it's going to console.log is the set itself. It's not an array of the set. It's going to return the full set. So if we run that, you can see here it's going to return the set, which is an object. And since it's an object, it's not going to show all the different items in the set. Okay, that's the set data structure. The queue data structure is a way to hold data. It's similar to a stack. While a stack is first in, last out, a queue is first in, first out. An example in real life is when you are waiting in line to buy something at a store. The first person to get in the line is the first person to get to the cash register. Another example is a print queue. When a lot of people are printing documents at the same printer, the documents are printed in the order they were sent to the print queue. In JavaScript, just like a stack, you can implement a queue with just an array. If you want to limit an array to just the traditional queue methods, you must create it yourself. Let me show you one such implementation. So we have the queue right here, and we're going to have a collection that's going to collect all the items in the queue, and this is just kind of a helper function to print or to console.log the collection. And here are the main methods of a queue. We have enqueue, which is going to push the first item onto the queue, and then we have dequeue, which is going to take an item off the queue. So there's two ways to do it with an array. Items can go into the array at the beginning of the array, or items can go in the array at the end of the array. In this implementation, items are going into the array at the end of the array, and then they come off of the array at the beginning of the array. To put an item onto the queue, we're just going to push that element onto the queue. Then, to dequeue, we're going to use the array.shift. .shift just pulls off the first item of the array. It removes the first item of the array and returns it. Another queue method is front. This is just going to return what item is at the front of the array without removing the item off of the array. So we're just going to do collection, just going to return what items at the 0 index of the collection array. And size, we just try to figure out the size of the queue. Pretty straightforward. Just collection.length, and then is empty. Check if it's empty, if there's no items in the queue. So let's see how that is going to work down here. I'm just going to uncomment that and run the code. So we created a new queue, then we enqueued A, B, C. So the end of the line is the end of the array. The beginning of the line is the beginning of the array. So it's going to print A, B, C here, and then dequeue means that the item at the beginning of the array is going to be removed. So the A is going to be removed, and then we're going to do queue.front, which I forgot to put the console.log here. If I run that again, you'll see that it's going to check what element's at the front of the array, which is B, and then we're going to print the array again. It's just going to be B and C because we dequeued A. Another way to create a queue is a priority queue. In a priority queue, not only do you pass the element into the queue, you also pass the priority of the element. So if all the priorities are the same number, it's going to behave just like a normal queue. But when you pass in elements at different priorities, the elements that are passed in with a higher priority are sent to the beginning of the queue. So all elements with priority 5 are ahead of elements with priority 4. But if elements have the same priority, it just behaves like a normal queue. So let me explain how the priority queue works. First, let me show you an example of this code down here where we're using the priority queue. So we're going to create the priority queue, and then we're going to enqueue something. And so we're going to pass in an array. The first element in the array is the item we want to put onto the priority queue. The second thing in the array is the priority. And so you can see I'm not pushing them on in the same order, 2, 3, 1. But if I run this, when we print the collection, it's going to print in the order of the priority. And just to show another example, let me add an item with the same priority as an item we already have. And if I run that, you can see these two items have the same priority, so they're in the queue in the order that they were pushed onto the queue. So everything's the same on a priority queue except the enqueue function. So in the enqueue function, first we're going to check if the queue is empty. If it's empty, you're just going to push on the element. But if it's not empty, you're going to have to check the priorities to see where to put the element on. So we're going to create a variable just to check whether we've added the item to the queue or not, and it's false. It starts at false. And now we're going to have to run through each element in the collection or the queue to check what the priorities are. So we have this for loop that's going to run through each item in the collection, and we're going to check is the element at index 1. Remember, the element that we pass into the queue is an array. Index 0 is the item you want to put into the queue, and index 1 is the priority. So is the priority of the element we're passing into the queue less than the priority of the item in the collection that we're checking? And see, we're using this I from the for loop. We're going to go through and check every item in the collection, and we're going to check the index 1, which is the priority of that item. And then, if the priority is less than the item, we're going to add that item or the element to the collection array. That's what this splice is doing. And then we're going to say added equals true. We're going to break out of the loop here, and then we're going to be done, except if the element hasn't been added, we are going to then push the element to the array. And the only thing that's slightly different is this dequeue method, and this, the way I did is kind of optional. You could return the entire element with the item and the priority, or you can do what I did, where I just return the item without the priority here. That's just index 0 of this value, which is the item that we got off the beginning of the array. Well, those are queues and priority queues. A tree data structure is a way to hold data that, when visualized, looks like a tree you would see in nature. Now, this is actually what we visualize a tree data structure to look like. All data points in the tree are called nodes. The top of the tree is called the root node, and from here it branches out into additional nodes, each of which may have more child nodes, and so on. Nodes with branches leading to other nodes are referred to as the parent of the node of the branches that leads to the child. Leaf nodes are nodes at the end of the tree that have no children. Also, any children of a node are parents of their own subtree. In this video, we will be covering a specific type of tree called a binary search tree. While the tree data structure can have any number of branches at a single node, for instance, see the C here? There's FGH. It has 3 branches at a single node. A binary tree, however, can only have 2 branches for every node. If we look down here, here's a binary tree. Each node only has 2 branches. Also, binary search trees are ordered. Each subtree is less than or equal to the parent node, and each right subtree is greater than or equal to the parent node. Because they use the principle of binary search, on average, operations are able to skip about half of the tree, so that each lookup, insertion, or deletion takes time proportional to the logarithm of the number of items stored in the tree. This is much better than the linear time required to find items by key in an unsorted array, but slower than the corresponding operations on a hash table. So let's see how this works in JavaScript. Here we're going to use classes to create the binary search tree. Basically we're going to create 2 classes, the node class and the BST or binary search tree class. The node class represents each node in the tree, and there's going to be 3 data properties. We have the data, which is what we're actually trying to store, and we have this.left and this.right, which are going to point to the left node and the right node. So in the binary search tree, we're going to have the constructor, which just creates the root node, which is the top of the tree, which starts as null, and then we're going to have the add function. So this is how we are going to add something to the tree. So we're going to add the data, we're going to get a reference to the root node, but if this is the first node, node will be null. In that case, we're just going to set the root node to the new node, the new data we just put in. So new node data. So we're just going to create a node based on that data. If it's not the first node, we're going to have to figure out where to put this node in the tree. To figure out where to place the new node, we are going to use a recursive function. So we're going to create this function, which is search tree. We're going to pass in the node, which starts off as the root node. If the data we pass in is less than node.data, that means we're going to put the node on the left side of the tree. So if the node.left side of the tree is null, we're just going to assign node.left to the new node, and then we'll return. But if node.left is not null, we're going to return search tree node.left. That just means we're going to continue searching. This is where the recursive nature comes in. It's going to run the search tree function again and continue working down the tree to find where to put the node. And you can see here, else if If the data is more than node.data, that means we're going to put the node on the right side. So if node.right equals null, then we just assign node.right to the new node, and we can return. Else if the node.right does not equal null, we are going to have to keep searching. So we're going to return search tree node.right. So else, that means data is not less than node.data, data is not more than node.data, so they must be equal. If they're equal, we're not going to add the data to the tree. We're just going to return null. So this is the search tree function, and this is how we initially call the search tree function. Return search tree node, which starts out as the root node, but then it can be called with different nodes as it's going recursively through the tree. Let's say you have 50 in your tree, and you have 17 in your tree, and you want to add 23. First, it's going to see that the node is not null because you have things in your tree. And then it's going to run the search tree function, putting in the root node, which is 50. Then we'll see if data is less than node.data, which it is because 23 is less than 50, we're going to go to the node.left. If node.left is null, we would put it here, but it's not because there's a 17 here. Remember, we're just adding the number 23. So else if node.left does not equal null, which is true, we are going to return the search tree node.left. So we are now going to run this search tree function, but pass in the 17. So now we're going to see, is data less than node.data? Well, now data is 23, but node.data is 17, so this is false. Now we're going to go down to this. Is data more than node.data? Yeah, 23 is more than 17. Well, is node.right null? In this example, we're saying that 23 isn't there, so node.right would be null. And then we can just set node.right to be the new node. The next functions we're going to talk about are find min and find max. So we're just going to be finding the minimum of the array and finding the maximum of the array. If you look at this binary search tree right here, you can see the minimum is all the way on the left side, 9. The max is all the way on the right side, 76. So just using that knowledge makes it easy to find min and find max. So we're going to set the current node to the root node, and so the min is going to be all the way on the left. So while this .left does not equal null, the current node is going to be current.left. And then at the very end, it's going to return current.data. So we're going to check this. If the left side is not null, we're going to go to the next one. If it's not null, we're going to go to this one. If it's not null, we're going to go to this one. Now the next is null because there's nothing to the left of 9, so we're going to return current.data. We're going to return the 9 because that's the data on the very left side. Find max is just the same way, but the opposite. We're going to start at current, which is going to be this .root, which is going to start at the top, while current.right does not equal null. Well, this does not equal null because it's 72. Then we're going to go to the next loop, current equals current.right. We're going to go to the next one, but now current.right is null because there's nothing to the right of 76, so we can just return current.data. Now we have the find function. Now isPresent is very similar, but instead of returning the node, we're just going to return true or false whether the data is in the tree. So we're starting at the top, the root node. While current, that means while there is a current node, while current is not null, we're going to do the following. If data equals current.data, return true. That means we found it. If we haven't found it, we're going to see is data less than current.data? Now current equals current.left. So we're going to start searching on the left side. Else, well, data must be more than current.data. So we're going to start searching on the right side. And we're going to keep searching. And if we never find it, if we never find that data equals current.data and return true, that means it's not in the tree and we can return false. Okay, the remove function is a little more complicated than the other functions we've covered. Just like in the add function, in the remove function, there's going to be a recursive function. So we're going to create this function here, const remove node equals function, where we're going to pass in the node and we're going to pass in the data, which is the data what we're trying to remove. So we have this whole function here, and then here's where we're going to call the function at the end. This.root equals remove node, and we're going to pass in this.root and data. We're assigning this.root to whatever is returned to this function here. We're going to pass in the root node, because you always start with the root node, and then the data that we're searching for. So let's see how that works. First of all, we have to check if we have an empty tree. If the node equals null, then we have an empty tree, and we can return null. Now we're going to see, does data equal node.data? So we're trying to see if we can find that data in the tree. So if we've found the node with the data, this is what we're going to do. There's actually 3 different options. Either node has no children. That would be just like the 76. If there's no children, we just completely delete that node. So if node.left equals null and node.right equals null, that means there's no children. Just return null. When we're returning null, we're setting the node that had that data to null. Now we're going to check if the node just has one child. If node has no left child, if node.left equals null, that would be just like this 54 here. There's a node on the right, but there's no node on the left. If node.left equals null, then we're just going to return node.right. That means we're going to replace this node with whatever is on the right, which is 67. So instead of 72 pointing to 54, that will be replaced with 54's node.right, which is 67. And if there's no node on the right, we're going to do the same thing. We're going to just return the node that's on the left to be the new node that's being pointed to. It gets more complicated when the node has 2 children, like such as 17. If you want to replace node 17, you can't just put in 12 here, because then what will happen to 23? You just can't just put in 23 here, because then what will happen to 12? So let's look down here at this picture down here. It's kind of small. Let's say we're trying to remove this 3 here that has the red X in here. The way to remove this node right here would be to replace it with this node down here. So if we remove 3, we can replace it with 4, and then everything will be right with the binary search tree. So if you look at what it would become over here, we just replace the 4 down here with the 3 up there. But how are we going to get down to that 4? Well, first we have to go to the right subnode, and then we have to go all the way down to the most left subnode after we've gone to the right subnode. So let's see that. We're going to create a temp node, which is going to be node.right. So in this case, the temp, if we're trying to delete the 3, the temp node would be node.right, which would be the 6 here. While temp node.left does not equal null, temp node equals node.left. That means we're going to go to the right of the node we're going to delete, and then we're going to keep going to the left until we get to the last one on the left side. And this one just happens to be 4. There's no more to go down because you just have to go down 1. But if there was more to go down, it would just keep hopping down until it got to the most left node. Now we're going to set node.data to temp node.data. So the node is the 3 up here. So instead of the data of this node being 3, the data of the node is now 4, because temp node.data is 4. Now we're going to set node.right to equal, and now here we're going to call the remove node function again. This is where it starts becoming recursive, and we're going to pass in the node on the right and the temp node data, and this will keep running through the function and set up the right side of the tree correctly. We see here we were saying if data equals node.data, else if data is less than node.data. That just means we have to go to the left side of the tree because it's less. And here we're going to say that node.left equals remove node, and we're going to call this recursive function again and pass in node.left and the data, and then we're going to return the node. Else, that means data is more than node.data. We're going to do node.right and then call this recursive function again and node.right data, and we're going to return the node. So you can see that delete is the most complicated one that we've covered, especially when one node has 2 leaves. So let's look at how you use a binary search tree, at least this one that I've created so far. So let's open up the console here. I'm going to do const bst equals new bst. I've created my binary search tree. We're going to add 4, add 2, 6, 1, 3, 5, 7. And then I'm going to remove 4, and then we're going to console.log the min and the max 2 times, and then we're going to check to see if 4 is present. Another thing we're going to do is I'm going to add in a remove 7, and we'll run that again. You can see at first the minimum is 1. It's going to console.log max, which is 7, but then we remove 7, and now the max is going to be 6, and we're going to see, is this present? Is 4 present? False. Nope, 4 is not present because we've removed it. This video covered all the key methods common to a binary search tree. However, in a future video, I'll be going over a few other things you can do, such as finding the tree height and traversing the tree through in-order, pre-order, and post-order traversal. If you want to play around with this code, you can check the link to the code in the description. I'm going to talk about finding the tree height and tree traversal. Height in a tree represents the distance from the root node to any given leaf node. So if you look at this example over here, the root node is 9, that's height 0. But if you see 4 and 17 here, that's height 1. 3, 6, and 22, height 2. 5, 7, and 20 are height 3. So it's the distance from the root node to the leaf nodes. They're kind of like layers of a cake, and that's how you're going to count them. Different paths in a highly branched tree structure may have different heights. But for a given tree, there will be a minimum height and a maximum height. And if the tree is balanced, these values will differ at most by 1. So before I show you the code to implement those things, I'm going to show you the use of the code. We're going to go all the way down to the bottom where we create a new binary search tree, and then we add all these values, which those values there are the same values as in the picture over here. We're going to find the min height, we're going to find the max height, and we're going to check if it's balanced. Let's just comment out these now. So it's showing the min height is 1 in the console, the max height is 3, and it's not balanced. The min height is the distance from the root node to the first leaf node without 2 children. So if you look on here, 17 is a root node without 2 children. It has a right child, but it doesn't have a left child. So the minimum height, you start at the root node, which is 0, and then you count to the next level, which is 1. So the min height is 1. Now the max height is just the distance from the root node to whatever the most bottom node is. So 5, 7, and 20 are all at the max height. So 0, 1, 2, 3. So the max height is 3. Now this tree is not balanced, because remember, if a tree is balanced, the values between the min height and the max height will differ at most by 1. You can see that there's a missing number here. The reason why this tree is not balanced is because there's no number here to the left of 17. But if I uncomment out this code here, we're going to add 10. Now 10, if you see, when it's being added, it's going to add to the left of 17 because it's more than 9, but it's less than 17, so the 10 will fill this spot right here. And then we're going to find the min height, the max height, and then check if it's balanced again. Okay, so now the min height is 2 and the max height is 3. The min height is going to be either this 3 or the 10 that we just added. It's not showing up in the picture, but just imagine there's a 10 right here. So we have 0, 1, and then the min height is this level right here, because this is the first level that there are nodes without 2 children, if you imagine there's a 10 right here. So that's 2, and then 3 is down here. Right now, is balanced is true. The difference between the min height and max height is at most 1. So it's going to have to be either 0 or 1 to be balanced. When a tree is balanced, then searching through it is much more efficient. We're not going to cover this in this video, but there are ways that you can make a tree automatically balance itself when you add new items and when you delete items. This creates greater efficiency when searching the tree. Okay, now we're going to look at these last lines I have commented out here. These are ways to traverse the tree. Tree traversal methods can be used to explore tree data structures and basically find all the values in the tree. In depth first search, a given subtree is explored as deeply as possible before the search continues on another subtree. When I show you an example, that will make more sense, but there's basically 3 ways that this can be done. There's in-order traversal, pre-order traversal, post-order traversal, and this last one I'm going to talk about later, this level order traversal. So let me run this and then I'm going to explain it. So here you look at the bottom of the console and you can see what we've logged here. For in-order traversal, you're going to begin the search at the leftmost node and end at the rightmost node. So you can see this just has all the numbers in order. 3, 4, 5, 6, 7, 9, 10, 17, 20, 22. Those are just all these numbers in order. You're going to begin at the leftmost node and you're going to add all the numbers in order. Now pre-order traversal, you're going to explore the root nodes before the leaves. So let's look at this. I'm going to read off these numbers down here and I'm going to show up on the picture where they are in the picture. So we're looking at the root nodes first. in the list, 9 is first, that's a root node, then 4, that's a root node, then 3, and the next root is going to be 6, and then 5, and then 7, then 17, and then 10, which we don't have on this picture, then 22, then 20. So the pre-order focuses on the root nodes first and then adds the nodes below that. The post-order explores the leaf nodes before the roots. So look at this one. The first node on the list is 3 because it's a leaf all the way down. And then we have 5 because that's a leaf node. And then we have 7. And then we're going to go to 6. We're not going to hop over to 20 over here because that's on a completely different branch of the tree. You have to finish all the leaf nodes on one branch before you go to the next branch. So after 6 is 4. Now is where we jump over the leaf nodes on the next branch and we use 10, which again is not on the picture, then 20, then 22, then 17, then 9. This level order is called a breadth first search. This explores all the nodes in a given level within a tree before continuing on to the next level. First it's going to do level 0, which is 9, if you see these numbers down here, and the next is going to show 4 and 17, then 3, 6, 22, then 5, 7, 20. So let's go over the code. So first we're going to go over the code for the min height and the find max height, and the is balanced. So the is balanced is pretty simple because you just call these functions that I haven't talked about yet, but you're going to call find min height and see if that's less than or equal to find max height minus 1. So this is going, since this is a conditional statement, it's going to return true or false. So as an example, if you remember before we added the 10, we had the min height of 1 and the max height of 3. If this dot max height is 3, 3 minus 1 is 2, so is 1 less than or equal to 2? No, false. So we know that the tree is not balanced. We have false right here. But then we run it again down here, and the max height is 3 and the min height is 2. If we do 3 minus 1, that's going to be 2. So now we have, is 2 less than or equal to 2? Yes. So we're going to return true. So that's how we're going to find out if it's balanced. Now let's look at find min height. This is going to be a recursive function. You can pass in a node, but if you don't pass in a node, it's going to set the node to the root node here. And then it's going to check if the node is null and return -1. If you haven't added anything to the binary search tree, it's going to return -1 for the height. We're going to set the left and right to calling the find min height on node.left and find min height node.right. So this is where the function becomes recursive. Eventually one of these two is going to be -1 because the left or right node is going to be null. So here we are going to add 1 to the left if left is less than right, and we're going to add 1 to the right else. So if right is less than left. And for find max height, it's the opposite. So instead of having the less than here, we have the more than here. So here we're going to return left plus 1 if left is more than right, else return right plus 1. Feel free to check the code in the description to play around with this yourself. The in-order, pre-order, and post-order, there's a lot of similarities to the code. So let's look at the in-order traversal first. The only thing that's going to be different in each of these in-order, pre-order, and post-order are these 3 lines. And the only thing that's going to be different in those 3 lines is the order of the lines. So for all of them, we're going to check if the root is null and return null. That's just to check if there's even a binary search tree that exists or if there's any values in it. So if we find out that there is a binary search tree, we're going to do these things. We're going to create a new array of the result, and we're going to add each value in the tree onto the result. So we're going to create this function, traverse in order function, and you can see down here we're going to call that function and pass in the root node, and then after the function has been run, you're going to return the result. So inside this function, it's going to be recursive. And remember, these 3 lines are the only thing different between in-order, pre-order, and post-order. It's going to change the order that we check things. So in order, we are going to first do this line. So this right here is short circuit evaluation. Whenever JavaScript evaluates the AND operator like this, if the first thing is true, it will also run the second command. If the first thing is not true, it will not run the second command. Check my video on short circuit evaluation to find out more about that. So if node.left is true, that means if node.left exists, then we are going to run the traverse in order function on node.left. And that just calls the same function again and passes in node.left. Then we're going to push node.data. So we're going to push the value in that node onto the result array. And then we are going to check if node.write exists. If it does, we are going to call the traverse in order function on node.write. And if we look down here, remember I said that just these three lines are different. So in pre-order, it's going to push first, and then it's going to call the function on node.left, and then it's going to call the function on node.write. In post order, it's going to call the function on node.left, then call the function on node.write, and then push the data. So just the order that we call these commands is going to change the order of how we get the result when traversing the tree. Again, you can check that code and play around with it until you can figure out exactly how it works. I'm going to go down to the level order function. In this method, we start by adding the root node to a queue. Then we begin a loop where we dequeue the first item in the queue, add it to a new array, and then inspect both its child subtrees. If its children are not null, they are each enqueued. This process continues until the queue is empty. We are creating a result array that we are eventually going to return. Now here's just the queue array. This is just a temporary array that we're using that we're eventually going to put things off that array onto our result. If this.root is not null, if there actually is a binary search tree, we're going to push the root node onto queue. This is a while loop, so it's going to continue going through this until we've actually added all the elements from the tree. So while queue.length is more than 0, we're going to keep doing these things. So first we're going to let node equals queue.shift. Now shift just takes off the first element in the array and returns that element. So we're going to put the root node into node because it started out as the root node, and now queue is not going to have that root node on it anymore. And we're going to push node.data onto that result. So we just pushed 9 onto the result. And if you remember, 9 is the first thing in the level order result. Now, if node.left does not equal null, we are going to push node.left onto the queue. And if node.write does not equal null, we're going to push node.write onto the queue. And then we're going to go back through the while loop. We're going to take off the first node and put it into node, which remember is going to be node.left that we push on here. And we are going to push that value to the result. So we're going to push 4 to the result. And now we're going to push node.left and we're going to push node.write. So in the queue, we're now going to have 3 and 6. But when we go back through the while loop and we shift off an element, even though we added 3 and 6 in the last iteration of the loop, the node that we're shifting off is going to be 17 because shift is going to take the first item of the array off, and 3 and 6 are at the end of the array. So then it's going to get that value, and so on. It's going to keep going through this until it's gotten every value from the tree. A hash table is used to implement associative arrays or mappings of key value pairs. Hash tables are a common way to implement the map data structure or objects. They are widely used because of how efficient they are. The average time for each lookup is not tied to the number of elements stored in the table. In fact, the average time complexity of hash tables in big notation is O of 1 for search, insert, and delete. That's very fast. The way a hash table works is that it takes a key input and then runs it through a hash function. A hash function basically just maps strings to numbers, and usually the numbers just correspond to indexes in an array. So for example, here are the strings. We pass through the hash function and then we get the numbers over here. A hash function needs to be consistent, so when you run a key through the hash function, it always gives the same number, and it should map different words to different numbers.
If two words get hashed to the same number, this is called a collision. You can see in this example, John Smith gets hashed to 2, Lisa Smith gets hashed to 0, 1, Sam Doe 4, and then Sandra D also gets hashed to 2. So this is a collision because both of these names, once they run through the hash function, get turned into the same number or the same index for the array. One way to handle collisions is just to store both key value pairs at that index. Then, upon lookup of either, you would have to iterate through the bucket of items to find the key you are looking for. This could take a little extra time because of the iteration. So here's another example where it's showing that the names are going through the hash function, and then it's showing basically the information that's being stored in the bucket. So this would be the array index, and in that array index or the bucket we would store the phone number. So this would be like a phone book. The numerical value from the hash function is then used as the index to store that information. Then if you try to access the same key again, the hashing function will process the key and return the same numerical result, which will then be used to look up the associated value, which just means that once you store all these things in the array, once you want to get the number again, you would just pass in the key John Smith into the hash function. It would give you the exact same array index 2, and then you would get the information returned to you, which is the phone number. Now you'll probably never have to implement hash tables yourself because most languages, including JavaScript, already have them built in. In JavaScript, hash tables are usually used to implement objects. However, it can be helpful to see how they are implemented just to gain a better understanding. So I'm going to show you the code for a hash table so you can see how they work. First of all, we have our hash function where we're going to pass in the string that we want to hash and then the max. Max is the number of buckets that we're using in our hash table to store values. We're going to start with hash being 0. And we are going to, for each character in the string.length, for as long as the string is, we are going to add the char code of each character. Each string character has a numerical value associated with it. So basically, we're just adding up the character codes for each character in the string and putting into the hash. Now, instead of returning the hash, we're going to return hash modulus max. That just means we are going to divide by the number of buckets and then return the remainder. So if we had 5 buckets, if we're dividing by 5, the remainder is either going to be 0, 1, 2, 3, or 4. And then that would be the index that we're going to place the item into the array. Now this is a very simple hash function, just for an example, but they can get much more complicated. Now let's go into the hash table function. So in the hash table function, we're going to have our storage array, which is where we're going to store all the data we're putting into it, and the storage limit. Now this is the number of buckets in the array. At first I'm just going to show you with just 4 different buckets, but normally actually this number will be much higher. And this is just a utility function just for this example, so I can easily print all the items in this storage array. I can easily log them. So here's where the real methods come in for the hash table if we want to add some information. So first you're going to pass in a key and a value. We're going to figure out the index of the array by running it through the hash function. So we create this hash function where we're going to pass in the key and the storage limit, the number of buckets that we're going to have in our hash table, and that's going to return an index that we went over before. If there's nothing in that index in the storage array, if it's undefined, we're just going to set that index to be this key value pair array. Else, if it's not undefined, that means there's already something in that bucket. So first we're going to set inserted to false, and then we're going to go through each index to see if the key already exists. If the key already exists, we're going to set the new value here and set insert to true. If the key does not exist, then inserted is still going to be equal to false, so we're going to push in the new item. That's where we'll get multiple entries into one bucket.
So the next thing is if we're going to remove an item from the hash table. So if we're going to remove, you just pass in the key of what you want to remove. And now we're going to look up the index by passing it into the hash function. If the index.length equals 1, that means there's only going to be one item in that bucket, and the item in that bucket equals the key that you passed in. Then you can just delete that index. You can just delete that item. But if it does not equal 1, that means there's probably a few different items at that index, and we want to only delete the item associated with that key. So we're going to go through each item in that bucket or in that index, and if the key equals the key we passed in, then we can delete that item. The 0 index is the key, the 1 index is the value. So let's go how we would look up an item. Again, we're going to set the index using our hash function with the key that we passed in and the storage limit. If the index there is undefined, we just return undefined. It's not, the item is not in the hash table. Else, we're going to go through each element in that bucket. If the element equals the key, then we can return that element. So let's look up a few examples. First, I'm going to show you an example of the hash function here. If we run that, it's going to be 3. And every time I run that, you'll see in the console 3, 3, 3. Every time I put bow, it's going to put 3. But if I put a different name here and I run that, you can see in the console it's going to be 5. And now every time I run that, it's going to be 5. So with this hash function, it's going to always be a number between 0 and 9 because we're passing in 10 as the number of buckets. So now let's actually see the hash table. So here we're going to create a new hash table called HT for hash table. We're going to add Bo, who's a person, add Fido, who's a dog, Rex, who's a dinosaur, Tux, who's a penguin. Then we're going to look up Tux, and then we're just going to print the entire thing. So let's see what happens in the console. So we saw that Tux is a penguin. Now let me bring this over a little bit. It's going to show our entire hash table. Now normally you're never going to print out the hash table like I did to the console, but I just did that just for learning purposes. If you remember up here, we have the storage limit set at 4. So we only have 4 buckets. The reason why I had it set at 4 is so we will see what it looks like when there's a collision, when there's 2 things in one bucket. Just by coincidence, the first bucket is undefined. That means none of these words hashed to 0. And then if we look at the second bucket, that's right here. There's actually 2 key value pairs in the second bucket. So both Bo and Tux both gave 1 when it went through the hash function. And then you can see in this bucket right here, we just have 1 item. And in this bucket right here, we just have 1 item. So when we pass in Rex to the hash function, we got 3 returned. But if we go up here and we change the number of buckets to something like 14, now I'm going to try running that again. If you look right here, now there's a lot more undefined because most of the buckets are now empty. But this bucket only has 1 item. That bucket has 1 item, and then the last 2 buckets have 1 item, and there are no collisions now. Each bucket only has 1 item. Now this has just been a pretty simple example of a hash table implementation, but it's enough to give you a basic idea of the hash table. A linked list is a common data structure where elements are stored in a node. The node contains 2 key pieces of information: the element itself, and a reference to the next node. So in this example, the element here would be 1, and then here's the reference to the next node. This arrow is pointing to the 2. This 2 is the element we're storing the information to, and then we have this link linking to the next node. Like arrays, linked lists can be used to implement many other data structures. Linked lists have some advantages and disadvantages when compared to arrays. Traditionally, arrays just have a fixed size, and linked lists have dynamic size. So you can just keep adding links and you don't have to do anything differently. JavaScript kind of hides some of this, but when you create an array, it can only be a fixed size. Also, arrays have pretty inefficient insertions and deletions, while linked lists are very efficient insertions and deletions. A benefit to arrays are the random access, which means you can say you want something at index 5 and you can instantly get the thing at index 5. However, with linked lists, If you want something at index 5, you have to go through every element in the linked list to get to index 5. And then for arrays, they may result in much memory waste. To make up for the fact that arrays can only be made at a fixed size, sometimes they will be created a lot bigger than what you really need to make sure you have enough room for everything. However, in a linked list, because of the dynamic size, there is no wasted memory. And then we have really fast sequential access for arrays and slow for linked lists. So every linked list is going to have a head. So we have this head pointer here that points to the first node, and then it's also going to have a size. So that's just the amount of nodes. So in this example here, the size will be 3. And you can see each node points to the next node, and the last node just points to null because there's no next node. So if you look at the code over here, we start with a head of null because we don't have a head yet, and the length is going to be 0. And the linked list is made up of nodes. So here's how we're going to create a node. We pass in an element, and this dot element is set to element. This dot next is set to null. So this dot element in the picture is the info, and this dot next in the picture is the link. So it starts off just like the last element, where the link is pointing to null, next is pointing to null. Then we just have a few simple functions. This dot size just returns the length, and this dot head just returns the head. And here's the add function. Whatever you're going to pass in to the linked list is going to be the element. So you're going to add the element, and then we're going to create a new node with that element. So after you pass in the element and it creates this new node, the element of the node is set to the element you passed in, but the next of the node is set to null. So if head equals null, that means there are no nodes in the linked list yet. So we just set the head to equal the node. And at that point there would just be one node in the linked list, and the head would be pointing to that first node. Else, that means there's more than one element in the list. We're going to set the current node to equal the head. And let's add a var in front of here. So this just means that we're going to start at the head node, which you always have to do. Whenever you're doing anything to a linked list, you start at the beginning, and then you have to go through each item in the list. While current node.next, that means while there is a current node.next, while current node.next does not equal null, you can see at the end, remember the link equals current node.next. So at the end, it equals null. So before the end of the list, the current node.next, which would be the link, does not equal null. It equals the next node. So this just means while there is a next node, current node equals current node.next. So that's just a way to hop from node to node on the list. Once there is no current node.next, that means we're at the end of the list. The end of the list is where we want to add the element that we're adding. Now we'll set current node.next to equal the node. Once we get to the last node in the list, we'll set the current node.next, or this link, to equal the new node we added instead of null. And we just increment the length. The remove method takes an element and searches the linked list to find and remove the node containing that element. So you're passing the element that you want to remove, and we always start at the head, current node equals head, and then we also need to know the previous node when you're going to remove something. So if the current node.element equals element, if current node.element equals element, well, that just means that the head node is the element we're trying to remove. So if we're trying to remove the head node, we just have to set the head to current node.next. So the head pointer will be pointing to the next node. If the head node is not the node we're looking for, we go to the else. So else, while current node.element does not equal element, basically while the node we're on does not equal the node we're searching for, previous node is going to equal the current node. Like I said, we have to keep track of the previous node, and then the current node is going to equal current node.next, which just means we're going to keep going through this while loop and keep jumping to the next node on the list until we find the node we're looking for. Let's say it's the second node on this example here. We're going to set previous node.next to equal current node.next. If we're trying to remove this second node, we're going to set previous node.next. So the previous node.next would be the first node. So that would be the link. The link is now going to not point to the current node. The link is going to point to the current node.next. We would skip over that node and point to the current node.next right here. and that's how a node would be deleted from the linked list. And then we just decrement the link. Now here's another quick function, is empty, return length equals 0. So if the length equals 0, we're going to return true. If it doesn't equal 0, we're going to return false. And you may want to know the index of a specific element. So we're just going to have to hop from node to node until we find that element and then return that index. So the current node is going to equal head, start at the beginning, index is going to start at -1. And so while current node, that means while there is a current node, while it's not null, we're going to increment the index. So at this point, if we start at the beginning, we've incremented the index, so where the index is now a 0. So if current node.element equals element, return index. So if the first element, which would be this info, equals what we passed in up here, we're going to return the index. So if instead of the head node, we're going to return the index 0. If not, current node equals current node.next, and then we're going to continue doing this while loop and just hop from node to node, and then we're going to eventually be able to return the index as we keep adding 1 to the index for every time we do the while loop. And if we go through all the whole while loop and don't find anything, we're going to return -1. That just means the element is not in the linked list. So we just found the index of an element. Now we're going to find the element at an index. That's just the opposite. You're passing in an index number and you're going to return the element. So we have current node equals head, count equals 0, and here's the while loop here. While count is less than index, that means we haven't gotten to the index we're searching for, increment count, and current node equals current node.next. So that means we hop to the next node. So we're going to keep going through every node in the list until count is not less than index. That means count equals index. So we've reached the right index, so we can just return current node.element. Now at, you're going to pass in the index and the element. In add, remember, you always add to the end of the linked list. But in add at, you can add in the middle of the list. So just like add, we're going to create a new node with the element we pass in. And the current node is going to equal head. We always start at the beginning. We need to keep track of the previous node. And the current index is going to equal 0. So if index is more than length, that means we've passed in an index that's way bigger than the actual length of the linked list. So we cannot add at that index and we return false. If index equals 0, that means we're trying to add the element to the head node. So we'll set node.next. Remember, node is a node that we just passed in. So the next element is now going to be the current node, which would be the current head node. And then we just set the head to equal the node that we passed in. Else, we don't want the index to be the head node. While current index is less than index, we're going to go through each index until we find the correct index. So current index increment, we're going to set the previous node to equal the current node because we want to keep track of the previous node. The current node is going to equal current node.next. We're going to keep going through this while loop until we find the correct node. So if we want to add a node as index 1, or the second node on the list, once we get to that index, we're going to set node.next equal the current node. So remember, node.next is the node we passed in, and we're going to set that to equal the current node, which would be this index right here. Then we have to set previous node.next to equal the node that we're passing in, and then we just increment the length. And the last function I'm going to talk about is remove at. Now remove at and add at are very similar. A lot of the lines are the same, except we're not going to create a new node. The current node is going to be the head, we need a previous node, the current index is going to be 0. Here is a slightly different thing. If the index is less than 0, or if the index is more than or equal to length, return null. So we cannot remove a negative index, and we cannot remove an index greater than the length of the list. If index equals 0, we're trying to remove the head node. So we just set the head node to equal the current node.next. So instead of the head pointer pointing to this node right here, the head pointer is going to point to the next node right here. Else, this part is just like the add at. We're just going to keep going through each element on the list, and once we find the element we want to remove, like let's say we're removing this second element at index 1, we're going to set previous node.next to equal current node.next. We're going to set the previous node.next, or this link is going to point to whatever was in the link to the current node. Or so this link is going to point to now this node right here. And we're going to completely take out this one. And then we're going to do length minus minus and return the node that we're removing. And now we're just going to quickly show an example of using the linked list. We're going to call the linked list conga because a linked list is kind of like a conga line. And let me bring up the console. So we're going to create this new linked list. We're going to add some items: kitten, puppy, dog, cat, fish. We're going to show the size. We're going to remove the third item on the list. So we'll run that. And see, we're going to remove cat. Now let's copy this. We're going to do element at. Then we'll try index at, and for the element we're going to put puppy. Oh, I mean index of. So we remove cat. Now we check the new element at 3, which is going to be fish. And the index of puppy is going to be 1. Kitten would be 0. Puppy is 1. And the size is 4. Well, that's the linked list. A trie, that's how this is pronounced right here. A trie, sometimes called a prefix tree, is a special type of tree used to store associative data structures. A trie stores data in steps. Each step is a node in the trie. This is often used to store words, since there are a finite number of letters that can be put together to make a string. A possible use case would be to validate that a word is in a dictionary. Each step or node would represent one letter of a word. So if you can see over here, this is an example of a trie. This word right here will be B-A-L-L, ball. The steps begin to branch off when the order of the letters diverge from the other words in the trie, or when a word ends. So if you get the word B-A-L-L, but you also have B-A-T, bat. So the first two letters, B-A, are part of the word ball and part of the word bat. And then down here you can have doll, do, dork, and dorm. If you look at the red stars, that just means it's at the end of the word. So the word do, you can see it's the end of a word, even though there are still letters in other words after the O. So let's look at the information in each node from the code here. Each node is going to have keys, which is just a new map. And this is the ES6 map structure. It's kind of like an object. It has just key value pairs. And in these keys, the key value pairs are kind of like the name of a folder in a directory structure. So if you can imagine these all folders, in the root node there is the keys map that's going to have B, D, and S. And each of the key value pairs are the B, the name of this folder is the key in the map, and the value of that key is the folder B, the actual contents of the folder B. And so the D is the key in the map, and the value, the key value pair, the value is going to be the actual contents of the folder. Each node is going to have a list of keys, which is just a list of all the other letters that are inside that folder or inside that node. And then we're going to have an end data. That just means, is this the end letter in a word? So in this picture, all of the nodes with a star have end set to true, and all of the nodes without a star have end set to false. Now we just have a setter function, set end is equals true, is end, so it's just going to return true or false if it's the end of the word. So now that we've looked at each node in the trie, let's look at how the code to the actual trie is set up. So we're only going to have three functions. We're going to have add to add a word to a trie. We're going to have isWord to see if a word is a word in the trie, and then print. This is more of kind of like a helper function just to print all the words that are in the trie. So before I go through the code, let me show you how it would be used. We're going to create a new trie, and then you can add the words like this. And then after you add all these words, and these are the same words that are in this picture over here, you can check if it is a word. Is doll a word? Well, doll is going to be a word. Is door a word? See, we have the word D-O-R in the picture, but there's no star on R because door is not an actual word, even though those letters are in the trie. And then dwarf, well, check D-O-R, and then there's no F, so that's not a word. And then you can just print the whole thing like that. So if I run that, you're going to see in the console down here, true, false, false, and then you can see the whole list here. So let's go back up to here.
First of all, we're going to create the root node, a new node, and then let's look at the add function. So this add function is a recursive function. So when you call it for the first time, you're going to put the entire word you want to add to the trie, and that becomes the input. And here it says node equals this dot root. That means if you pass in a node, it will use that node, but if you don't pass in a node, it will just use this dot root as the default node. So if input.length equals 0, that means if we're at the end of the word that we passed in, we're just going to do node.setEnd and then return, and we're done with the add function. Else if, that means if there's more than 0 letters that we've passed into this add function, we're not at the end of the word. So first we're going to check if there's already a node with that letter that we're looking at. So this says if not node.keys.has. So let's say we're in the root node. Node.keys is a list of all the letters that that root node points to. So if it does not have a letter, input 0 would just mean the first character of the string we passed in. So if we pass in ball, this is just saying if there is not a node with the letter B here, then we are going to create a node with the letter B. Node.keys.set. Set is how we're going to create a new key value pair in the keys map. We're going to set it with the key to be the letter, input 0. So input with 0 in brackets just means the first letter of the input we passed in. So if we pass in ball, the first letter is going to be B. And so remember, each key value pair is kind of like the name of a folder and the contents of the folder. The name of the folder is B. The contents of the folder are a new node. So then this is where it becomes recursive. We're going to call this.add, and we're going to pass in input.substr1, which takes the input and takes every letter after the first letter and passes it into the add function again. So if the word was ball, every letter after the first letter is ALL, so we're going to just pass in the letters all, and we're also going to pass in a node. Before, remember, we start with the root node. Now we're going to pass in this node, which is also the node we just created here. So we're going to set a node with the letter B. That would be the input 0. So now we're going to get the node with the input 0. That's the first character. So now we're going to run the add function, but instead of being at the root node, we're going to be at the node B. And then the else is just if there's already a letter by that name. So remember here, we added a node with the letter B, but if there already is a letter B, like for instance, let's say we already have the word doll, and we're going to add the word dork. If we're at the D and the word doll is already in the trie and we want to add dork, well, O is already going to be in the trie. So if O is already in the trie, we're not going to create the O node. We're just going to add the new substring, which in this case would be ORK. We're going to add that to the node.keys.get at input 0, which would be the O node. So we're going to keep running through that until we've added the word to the trie. And then down here, we're going to check if the word is in the trie. So this is where the trie really performs. You can check if a word is in a dictionary much quicker in the trie than other data structures, because we don't have to check through every word, we're just checking one letter at a time. So we're passing in the word, we're setting the node to the root node at first, and then this is the loop that we're going to keep running through until we find the word. So while word.length is more than 1, while there's more characters to search in the word that we passed in, so if not node.keys.has word, this is saying we're going to check the first character in the word. So let's say we're on the root node. So if there is no key with the first character in the word, like let's say we passed the word tree, well, there's no T, there's no key with the letter T here, so we can return false. We quickly determine that that word tree is not in this trie because there's no word that starts with T. Else, that just means there must be a word that starts with that letter. So let's say we're looking for the word send. Well,
if it does have the letter S, then we're going to do these two things. We're going to set the node, remember which used to be the root node, but now we're going to set the node to the node S. Because if we're going to look for the word send, we're setting the node to the S node, and we're going to change the word into the word minus the first character. So now we're just going to be looking for the word end instead of send. So we're going to go back up here. Now we're going to keep running through this. Now we're on the S node, but we're looking for the word end. And yeah, we'll find the E, we'll find the N, and we'll find the D. And now we go to this very last line, if node.key.has word, which would just be a single letter, because remember we keep taking the letters off. And so if it has the last letter of the word that we passed in, and it is the end, so is end, then we're going to return true. That word is in the trie. Else we're going to return false. Yeah, so this last one was just the print function. This is just kind of a helper function. And so we're going to create an array of every word, but right now it's just going to be empty. Then we're going to search. We're going to pass in, and we're going to search. If we don't pass anything here, it's going to set this to the root node. Actually, I bet we don't even need this. Let me just run that just to see if it does the same thing in the console. Yep. We don't even need to set the node to the root node because when we first call the search command down here, we already pass in this .root. So we're just going to pass in a node, and we're going to pass in a string here. If node.keys.size does not equal 0, that means there's still more letters to look through. So for each letters in the keys here, let's say we're on the root node, so the letters in the key would be B, D, and S. So for each of those letters, we're going to run the search command again, and then we're going to pass in node.keys.getLetter. That means we're going to pass in the node at that letter, so we would pass in the B node, and then we're going to add that letter to the string. At the beginning, the string would be empty. So we'll do string.concat. That means we're going to add one letter. We're going to add the letter B. And basically, since this is recursive, it's going to keep going and keep adding each letter. It's going to keep concating each letter to the string until it's formed the whole word. And then see if node.isEnd, if we've gone to the last node in the word, it's going to do words.push string. So that's our words arrayed. If we've gone to the last letter in the word, we're going to push the word onto the words array. Now else, that's the else to this if statement. If the node.keys.size does equal 0, then we're at the last letter of a branch. If string.length is more than 0, we're just going to push that word on to the words array, or else returned undefined. And here's where we call that search function for the first time. So here's the search function, and then we call it for the first time, and it's just going to go over and over until it gets every word in the trie. If words.length is more than 0, it's going to return that the words array, or it's going to return null if there's no words in the array. So that's a trie.
A binary heap is a partially ordered binary tree which satisfies the heap property. It has some similarities to a binary search tree, except the order is a little different. Each node has at most 2 child nodes. The heap property indicates a specific relationship between the parent and child nodes. You may have a max heap in which all parent nodes are equal than or greater to the child nodes. So you can see the biggest numbers on top and the smallest numbers are on bottom. Or you may have a min heap in which all child nodes are greater than or equal to the parent nodes. So the child nodes are the biggest ones and the parent nodes are the smallest ones. The order between child nodes on the same level does not matter. So you have 10, 6, and 12 here. Here we have 5, 6, and 1. You can see that it goes from a small number to a big number to a small number. The order doesn't matter if they're on the same level. Binary heaps are also complete binary trees. This means that all levels of the tree are fully filled, and if the last level is partially filled, it is filled from left to right. So if you see the example down here, so here's level 1, then we have level 2 here, level 3. Level 3 is all the way filled. Level 4 is only partially filled because there's nothing over on the right side here, but you can see it's filled from left to right. Binary heaps may be implemented as tree structures with nodes that contain left and right references, like what I showed in my binary search tree video. However, heaps are more often implemented as arrays. This is possible because of the partial ordering according to the heap property. We can just compute the parent-child relationship of the elements. Now this will make a lot more sense with this diagram here. So if you see this array right here, this is the array representation of this tree right up here. The number 1 is 20, and that's the root. You can see that right up here. And then 2 and 3 are the child nodes, 19 and 17 right here. And now I want to pull your attention over to these equations up here. So the left child is going to be I times 2. The right child is going to be I times 2 plus 1. Let me show you what that means. So if you look at 20 here, which is at index 1 in the array, also I should point out that there is no index 0. So when you're representing a heap, you're just going to leave index 0 as null to make the math work out a little better. So if we go back to index 1, well, the equation for the left child is I times 2. So 1 times 2 would be 2. So yeah, 19 is the left child. And the right child is I times 2 plus 1. So 1 times 2 plus 1 is 3, 17. That's the right child. Now let's say we go to number 13 here. That's index 4. Well, if we go to the equation, I times 2, 4 times 2 is 8. So if you're at index 4 and you go to index 8, 11, yep, that's the left child. Now if we start at index 4 and we do the right child equation, I times 2 plus 1, that's 9. So if we go to index 9, yep, that's the right child here. So that's how you can use these equations to find the left and right child from an array representation. You can also figure out the parent. So the equation for a parent is I divided by 2. If we are on 11, that's index 8. 8 divided by 2 is 4, index 4. And this really should be floor I divide by 2 because you divide the index by 2 and then round down to the nearest whole number. For instance, 5 divided by 2 is 2.5, but if you round down it's 2, and then 2 would be the index 19 here. Also, you can see in this diagram that the last index is also the size of the heap, size 10. This diagram is a max heap. I'm going to show you the code for a min heap. But in the same file down here, I also have the code for the max heap down here. So you can check the link in the description so you can review this actual code yourself and you can review the max heap on your own. But like I said, we're just going to review the min heap right now. But before I show you the actual code, I want to show you a visual representation of how it works when you're inserting and you're removing items from the heap. Those are the main two commands, insert and remove, and then there's one more I'll show you at the end. But let me show you this representation here. So you can see this is the array representation, and I'm going to insert some numbers, and you'll see them show up as a tree representation. So let's see, 4. You can see 4 goes at the top, that's the root node. Now I'm going to put in 6. 6 just goes down to the bottom there. 8. So as it builds the node, one thing to keep in mind is that it's going to build one level of the tree at a time. I'm going to put in 10. It's going to be on the very left side. Now so far I've been putting them in order, but now I'm going to put in the number 5 here. And when I insert the number 5, you're going to see this. It's going to first go to the end of the array here. You'll see the array, which is going to first appear right down here. And then it's going to move it up to the correct position. So let's see that. So then, as you see, it checks what position to move it up to. So I'm going to put in a few other numbers here. Let's see, 16, 3. Okay, so you see it always puts in at the end of the array or the end of the tree, and then it moves it up to the correct position. Now I'm going to just show one more where I put in 1, where it's going to put it down here, and it's going to move it all the way up to the top. And it's a check one at a time to see if it has to move it up. Also, another thing would just be removing. When you remove, you always just remove the smallest. It's going to remove what's in index 1, which is always going to be the smallest, and then it's going to pop the last node to the first node, and then it's going to sort them. So let's see how that works. So did you see that? So it moved the last node to the first node, and then it has to keep checking and keep moving it down until it gets to the right position. So let's remove 3. Okay, so now let's go to the code and you can see how that works in the code. So before we insert anything, you can see that we've created a heap with an array that just has one item, and it's the item null at index 0. So when we insert something, we pass in a number, and we're going to push that number onto the end of the heap. So if you pass in the number 3, there's going to be index 0 is null, index 1 would be 3. Now, if the length of the heap is more than 2, that means there's more than one item in the heap. If it's less than 2, there's 1 or 0 items in the heap, and that makes things really easy. But let's say it's a more than 2. So we're going to let the index equal heap.length minus 1. So that means we're finding the last index in the heap, while heap at the last index is less than heap. And then see this equation right here? That is the parent equation. So now we're saying if the last item in the array, which is the item we just inserted right here, if the last item in the array is less than its parent, well, if it's less than its parent, we're going to have to move it up because the smallest numbers have to be at the top in the min heap. So if the index is more than or equal to 1, that means if we haven't reached the root node, then we're going to do this. Now this is ES6 destructuring syntax, which just means we are going to switch the node we just inserted with the parent node. We're going to switch them. So here is the parent node, here is the node we just inserted, and now we're going to switch them. So the node we just inserted is going to be first, and then the parent node is going to be next. So it's just a way to swap them. For more information about the ES6 destructuring, you can check out my video about that topic. So if math.floor index divided by 2 is more than 1, this just means if the parent node is not the root node, because remember this is the equation for the parent node, 1 is the index of the root node. So if the parent node is more than the root node, then we're going to set the index to math.floor index divided by 2. That's the parent node, which, if you remember up here, we just put the number we passed in into the parent node. So now the index is still going to refer to the number we just passed in because that number has went into the parent node, and so now we're going to set the index to that node. And since this is a while loop, we're going to keep going through this, and we're going to keep switching the node to its parent node as long as it is smaller than the parent node, else break. So once it's not smaller than the parent node, we just get out of this while loop, and that's the insert. So let's go down to remove. It's a little more code, but it's some similar concepts. So we are always going to remove the top node, the smallest node. So we're going to let the smallest equal heap 1. So that just means that the first node in the array is the smallest node. So that's the easy part. The hard part is rearranging the array after you've removed that node. So if heap.length is more than 2, that just means we have more than one node in the tree. We're going to set the first node in the tree, which remember was the smallest node, but we're going to set this to the last node. The last node in the array now gets moved to the first node in the array. Now we're going to do heap.splice, heap.length minus 1. This just shortens the array by 1, so we just removed the last index of the array completely since we've already moved that to the first index. If heap.length equals 3, that means there's only 2 numbers in the tree, and that makes things really easy. Just if one is bigger than the other, then we just switch them. This is the destructuring syntax again. So if the first one is bigger than the second one, then we switch it so the second one is bigger than the first one. And then we just return the smallest. If there are more than 2 nodes in the array, that's where it gets slightly more complicated. So we're just going to set the index to equal 1. We're going to set the left to equal 2 times I, and the right to equals 2 times I plus 1. Remember, that was just the equations from up above. The equations right here, we're just putting them into our formula down here. Now technically, you would not need to put this equation here since we know that I equals 1. You could just put 3 here, you could just put 4 here, but this is just so you know we're using the equations from above. So remember, 1 is the root node, so we're starting with the root node. So while the root node is more than or equal to its left child, or the root node is more than or equal to its right child, we're going to do everything in here. That means we're going to have to basically move it down. We're going to keep moving it down until we get to the appropriate spot. So if the left node is more than the right node, then we're going to switch the root node with the left node. This is the destructuring syntax again, so we're going to just swap the nodes. So for instance, we would be swapping, if we were on this node and this node, we just swap those two nodes, and then we're going to set the index to the left node. So we're going to set the index to be the node that was at the top node but has now been swapped. Else, that means the right node is less than the left node. We're going to switch the node with the right node. So we're just going to swap with the right node, and then we just set the index to be the right node. So the node just moved down a little bit, and then we set the index to point to the node that we just pushed down a little bit, and then we have to set the new left and right node. So we would set the left and right node to be the left and right of the one we just passed down. And then, if the left child or the right child equals undefined, that means we're at the very bottom of the tree, so we can just break out of this while loop. And if it's not undefined, we just keep going through until we find the place where the node that we're moving down the tree is not more than or equal to the left node and is not more than or equal to the right node. Else if the length equals 2, that means there should be only one element in the array, so we just cut off the last element. Else we return null. That means there were 0 elements in the array to begin with, and then we're just going to return the smallest element, which is just the element we just set up here. The last thing I'm going to talk about is this. Now, a common use case for the heap data structure is for heap sort. This is one of the most efficient sorting algorithms with average and worst case performance of O of n log n. Heap sort works by taking an unsorted array, adding each item in the array into a min heap, and then extracting every item out of the min heap into a new array. The min heap structure ensures that the new array will contain the original items in least to greatest order. So this is the function that you would use to do that heap sort. The hard part is creating all the code we just already went over, and this is just going to use that code. So let result equals new array. Well, heap.length is more than 1. We're going to do this.remove, so we're going to remove the element on top of the tree, and we're going to push it onto the result. And we're going to keep doing that until we've removed all of the smallest elements and push it onto the result, and it's going to put the elements in order. Well, that's all I'm going to talk about for heaps. Feel free to check out this code and create your own heap and add some items and remove some items just to see how it works. The graph data structure is not the same as a graph you may have learned about in math class. Graphs are collections of things and the relationships or connections between them. The data in a graph are called nodes or vertices. The connections between the nodes are called edges. One example of graphs is a social network, where the nodes are you and other people, and the edges are whether two people are friends with each other. There are two major types of graphs, directed and undirected. Undirected graphs are graphs without any direction on the edges between nodes. Directed graphs are graphs with a direction in its edges. An example of an undirected graph could be a social network. The nodes are people and the edges are friendships. An example of a directed graph could be the internet and web page links. The nodes are web pages and the directed edges are links to other pages, which might not necessarily point the other way. I'm going to show you 3 ways to represent a graph. The first way is called an adjacency list. This representation for a graph associates each vertex in the graph with the collection of its neighboring vertices or edges. In this image, A is connected to B is connected to A and C is connected to B. This is how you could show a relationship with text. And here is how you could show this adjacency list with JavaScript. This is an undirected graph because it does not show the direction of the edges. This can also be more simply represented as an array where the nodes just have numbers rather than string labels. Another way to represent a graph is to put it in an adjacency matrix. An adjacency matrix is a two-dimensional array where each nested array has the same number of elements as the outer array. So it's basically a matrix of numbers where the numbers represent the edges. Zeros means there's no edge or relationship, and ones means there is a relationship. This table shows an adjacency matrix to represent the image. You can see that the labels for the nodes are on the top and left. Now here's a JavaScript representation of the same thing. Unlike an adjacency list, each row of the matrix has to have the same number of elements as nodes in the graph. Here we have a 3 by 3 matrix, which means we have 3 nodes in our graph. An adjacency matrix can be used to represent a directed graph. Here's a graph where the second node has an edge pointing toward the first node, and then the third node has an edge pointing to the second node. Notice how the numbers in the array change. There are only ones where a node is pointing toward another node, and since there are only 2 points, there are only 2 nodes. The final way I will show to represent a graph is an incidence matrix. Like the adjacency matrix, an incidence matrix is a two-dimensional array. However, the rows and columns mean something else here. The adjacency matrix uses both rows and columns to represent nodes. An incidence matrix uses rows to represent nodes and the columns to represent edges. This means that we can have an uneven number of rows and columns. Each column will represent a unique edge. Also, each edge connects 2 nodes. To show that there is an edge between 2 nodes, you will put a 1 in the 2 rows of a particular column. As you can see in the diagram, edge 1 is connected to nodes A and B. Now look at the column for edge 1 in the incidence matrix table. You will see a 1 in both the A row and the B row. This shows that edge 1 connects to nodes A and B. Here is a directed graph. For a directed graph, use 1 for an edge leaving a particular node and -1 for an edge entering a node. And here is a JavaScript implementation of the incidence matrix. Graphs can also have weights on their edges. So far we have unweighted edges, where just the presence and lack of edge is binary, 0 or 1. You can have different weights depending on your application. A different weight is represented as a number greater than 1. Well, now you know about the different types of graphs and how to represent them in JavaScript. I'm going to talk about how to find the distances between 2 nodes in a graph. This is one of the main uses of graphs and is called graph traversal. Traversal algorithms are algorithms used to traverse or visit nodes in a graph. The main types of traversal algorithms are breadth-first search and depth-first search. In this video, I will be showing how to implement breadth-first search in JavaScript. As you can see, the algorithm starts at 1 node, first visits all its neighbors that are 1 edge away, then goes on to visiting each of their neighbors. The point is to determine how close nodes are to a root node. There are different ways to implement breadth-first search. In this version, you pass in an adjacency matrix graph and the index of the root node. Remember, in an adjacency matrix, each nested array in the matrix shows which nodes in the graph are connected to the node at that index. For example, this array is at index 0, so it shows which nodes that node 0 is connected to. If it is connected to a node, there is a 1 at that index, but if it is not connected, there's a 0 at that index. Before I go through the code, let's see it in action. So here is a graphical representation of this adjacency graph. Check out my previous graph video to see how this adjacency graph goes into this graph. So we ran the breadth-first search function, we passed in this graph up here, and then we passed in the number 1. So that means we're trying to find out how far away every node is from the first node. So you can see this graphical representation of the exact same graph. And if you see the first node right here, that's the node we passed in to the breadth-first search function. We're going to see how far away each node is. So you can see right here, it shows how far away it is. So node 0 is 2 nodes away. See, because of the direction of the graph, we can't just go straight across a 0. First, from 1 we go to 2, then we go to 0. So that's 2 nodes away. 1, the node itself is always 0 nodes away. And then the second node is 1 node away, just 1. Third node is 3 nodes away. See, first you have to start at 1, then you go to 2, then 0, then 3. So that's 3 hops. And 4 is infinity, because when you're from the first node, it's impossible to get to the fourth node, because the fourth node only points back to the first node. This function will output an object of key-value pairs, where a key is the node and the value is its distance from the root. This object will be used to store the distances to the root node. We will start all the distances at infinity, which in this version of breadth first search indicates that a node is not reachable from the start node. Here, the distance to the root node from the root node is set to 0 instead of infinity. We are going to create a simple queue to keep track of nodes to visit. And the purpose of this variable is to keep track of the current node that we are traversing. Now we will start a while loop to keep traversing nodes until there are no more nodes in the queue to traverse. We'll start the loop by popping off a node from the queue to traverse, which at the beginning is the root node. Here we get all the nodes connected to the current node. Remember, each index of the graph is an array that shows what nodes are connected to the root node associated with that index. So, in this example, we are first looking at node 1. At node 1, the array shows that it is connected to nodes 0 and 2. Now, we set the neighbor index variable to an empty array. This will keep track of a list of nodes that are connected to the current node. This line gets the first node connected to the current node. When it says index of 1, this finds the first connected node because the number 1 in our array means that the node is connected to another node at that index. If there is no node with an index of 1, the index variable will be set to -1. So, while index does not equal -1, push the index onto our list of neighbors. This line searches for the next connected node. We look for the next one in the array starting after the previous one we found. That's what this +1 means. Now that we know all the nodes connected to the current node, we loop through these connected nodes and get the distance. If the value in the nodes_len array at the index of the neighbor from the neighbor index array equals infinity, that means we haven't set the distance of that node yet. So we will set it now. We are going to set it to the value of the node's length array for the current node +1. Then we'll push that neighbor to the queue, so the next time we go through the while loop, we'll check the neighbors of that node too. This for loop is the most complicated part of this, and you may have to read through it a couple times to completely understand it. At the end, we return the node's length array. And that's breadth first search of a graph. Thanks for watching. My name is Bo Carnes. Don't forget to subscribe, and remember, use your code for good.